so we can see the light at the end of the tunnel. So Unit 9 is on models of chemical bonding. So at its core, we're really going to revisit ionic bonding and covalent bonding. And then this is going to allow us to transition us into the last two learning units for General Chemistry 1, which has to deal with thinking about the structures of molecules as we create covalently bonded substances. So that'll be the last two learning units. So two skills that we're going to have from this 9th learning unit on models of chemical bonding. And they're really split up by thinking first about ionic bonding and then lattice energy. And then our second skill will be on covalent bonding and bond energy. So when we think about this first kind of skill here, we're just going to do a brief revisit of how we know what goes on here with forming compounds. And I know we discussed this at the beginning of the semester, but I want to make sure that we revisit it here. We know that we have an ionic compound if we take something from the left and then the right side of the periodic table, a metal and then a nonmetal. If we take two nonmetals, two things from the right side of the periodic table, we're making a covalent compound. And then two things from the left side of the periodic table, we really haven't talked about that, but two metals, or allowing us to have metallic bonding, which we'll just touch on very briefly. That's when we just have stuff from the left side of the periodic table. So a lot of things that allow us to think about what is going on here has to do with thinking about two properties we talked about in our last learning unit on ionization energy and electron affinity. So again, ionization energy has to do with how much do you want to give up an electron, and electron affinity has to do with how much do you want to take on an electron. So when we have things that really want to give up electrons, like metals, pairing up with things that really want to take on electrons, like nonmetals, that's how we form our ionic compounds. Remembering that where we find things on the periodic table is really going to allow that to be our best cheat sheet. So when we think about types of bonding here, right, ionic bonding, metal and nonmetal, and again, that's a transfer of electrons from the metal that's willing to give up the electron to the nonmetal who wants to take on the electrons. When we're thinking about covalent bonding, two things from the right side of the periodic table, they both want to take on electrons. Nobody wants to be the giver of electrons. So really what we have there is a sharing of electrons. And as we'll talk about as we get towards the latter end of this chapter, sometimes that sharing isn't quite equal. Okay, so we'll talk about what that means. I'm not going to spend much time talking about this here, but when we have metals, there is attractions between individual atoms that we have in a metal sample, for example, and we talk about that as electron pooling. Really not going to get too much into that, but I do want you to know that there is a kind of bonding called metallic bonding. I want to introduce something here that's going to lead us into creating structures of larger substances and compounds in our next learning unit, and that's learning how to write and use Lewis dot structures. Right now in this learning unit, we're just going to create Lewis dot structures for individual atoms. When we move into our next learning unit, we're going to make Lewis dot structures for compounds. So this is kind of setting us up for how we think about that. A Lewis dot structure basically just has an elemental symbol that's written at the center, and then we put dots around the element to indicate the number of electrons. And as we know, that correlates with the number of valence electrons, which we can get from the periodic table. So for metals, the number of dots represents the number of electrons an atom would lose to form a cation. And so we can see here things that are in group 1 are going to lose that single valence electron to form their +1 cation. 2 electrons, 3 electrons, and so forth. So I think you see the trend here between the numbers 1 and 8. Nonmetals, again, having total number of unpaired dots representing the number of electrons that an atom would gain to form an anion or share to form covalent bonds. So again, the total number of unpaired dots, right? Here we can see unpaired dots that we have there. That represents the total number of electrons that we'd want to gain. So 2 unpaired electrons, oxygen's going to gain 2 electrons, or as we'll see in our next learning unit, it likes to form 2 bonds. Don't worry if that doesn't make a lot of sense yet. We'll get to that in our next learning unit. But all of this has to do with this magic number of 8, right? Everybody wants to be like a noble gas. They want to fill their electron shells either by gaining or losing electrons so that they have that magic number of 8, or they'll share electrons so that they feel like they have 8. Okay, so we're going to think about that in just a little bit here. But just again to highlight, this is something that we will build on, this idea of Lewis dot structures. Dots representing electrons, and when we build these together to make compounds, those electrons will form bonds. All right, so kind of combining some skills from things that we've learned in previous learning units here. We can think about, we've already done this, thinking about forming ions when we have the loss of electrons. So again, the lithium ion here is going to lose that one s electron. In this case, it's showing it as giving it to fluorine to make fluoride. And so we can see the electron configurations that we have of these respective ions after they've traded electrons. We can also show that same situation happening with atomic orbital diagrams. And so a lot of this is going to kind of come together in our last two learning units here. And so we have this ionic compound that's formed between lithium and fluorine when we form lithium fluoride here. So just kind of a nice review of some things that we've seen already, but applied to, in this case, the concept of ionic bonding. All right, this is going to be the big skill thing that you'll have. The question that you're going to see on the quiz from Unit 9 is either going to be an enthalpy calculation based on an ionic compound, so we're going to call this lattice energy problems, or you might see a problem that's related to bond energy and covalent bonding. So these problems sort of operate the same way, and we'll do one problem each day. When we have our in-class day for this first skill, we're going to do sort of a meaty lattice energy problem. So I'm not going to go through the details of the calculation. I'll kind of show you some pieces of it, but I want to highlight for you that it really is just an application of Hess's law and thinking about delta H of formation. So thinking about this, and I hope this picture looks a little bit scary, but let me just kind of break it apart for you. If we think about starting, and we're going to make a delta HF equation. So if we wanted to make lithium fluoride and make a delta HF equation, let's go ahead and write that down here. If we wanted to make lithium fluoride and we wanted to write a delta HF equation, remember, we are going to have a delta HF equation makes 1 mole of product from its corresponding atoms in their elemental form. So it's going to be lithium solid, and then fluorine comes as a diatomic gas, so we need to have 1/2 mole of it. All right, so remember with delta HF, we had to think about, well, how does this whole process happen? You know, it's like Lego bits. We're going to break everything apart and then reform our new stuff. And I want you to have that concept in your head. So let's think about the things that have to happen to take solid lithium and fluorine gas and make it into a lithium cation and fluoride anion. Okay, so you don't have to remember and like walk through this process, but hopefully it'll make sense for you. So here's some of the things that we have to do. The first thing that we need to do is we need to take lithium as a metal and we need to make it into a gas. And so we're going to basically be taking lithium solid and making it into lithium gas. And so that's kind of this first step that we have here is this what we call atomization of the metal. That's going to take some energy. So here's our first step upwards. Okay, the next thing that we need to do is we need to take and we need to split apart this fluorine gas. So it was fluorine as 2 fluorines together. We need to make it as single atoms. So look what we've done here. We've taken the solid metal and we've made it into gaseous metal. Doesn't sound like something normal, but remember, this is a thought exercise here. We're going to take this fluorine gas that's diatomic and we're going to make it into individual fluorine atoms. Okay, now the next thing that we need to do, look here, this is a term we've seen before, ionization energy. We need to take this and we need to remove an electron from lithium. So we're going to take lithium here and we're going to make it into lithium as a cation. All right, the next thing that we need to do is electron affinity. We learned about that in our last learning unit as well. So now we need to take this fluorine here and make it into fluoride. And so we're going to take and we're going to remove an electron there and make this into fluoride. Okay, so that's favorable. Remember, we talked about electron affinities tend to be exothermic. So that's kind of our first step down. Now look what we have here. We've got lithium ions in the gas phase and fluoride ions in the gas phase. Have you guys ever heard of salts wanting to be in the gas phase? No way. So we've got a huge downhill energy that takes these ions as gases and allows them to become a crystalline solid. Okay. So that's the whole process. And I don't need you to remember exactly what went on here. It was a good opportunity to review some of the concepts that we've talked about, whether they're ionization energy or electron affinity. But this is the important piece that we want to talk about here. Lattice energy. Lattice energy is that energy associated with separating a crystalline solid into its gaseous ions. So notice here, this is negative lattice energy. So when we gain energy back, when we take those gaseous ions and allow them to form their crystalline salt, that is lattice energy. Actually, the negative of lattice energy. We define lattice energy as the energy that it would take to break apart a salt into its gaseous ions. Crazy amounts of energy. Look at how big this arrow is. So keep in mind, every one of these little arrows represents a piece of information that could be used in a Hess's law calculation. Now, don't be scared when I look at this here, right? This is just a big Hess's law problem. All of these represent individual processes that were on the last slide. Notice here, this delta HF, that's really what this is. This is our delta HF. So if we wanted to figure out what delta HF is, we could put in all of these costs, put in all of these gains, and we could solve for delta HF, okay? Or if you knew what delta HF was, because you looked it up in Appendix B, you could actually solve for what the lattice energy is. Or you could solve for any one of these delta H's. Keep in mind, this is 1, 2, 3, 4, 5, 6 arrows that all need to sort of sum up, right? That's what Hess's law is going to be. One of the potential problems is you getting all the different equations and having to figure out how you'd rearrange them, Hess's law problem, to answer and give the one piece that's unknown. You know, one of these is going to be an unknown enthalpy. So again, we're going to have time to practice a problem like that in class. But one last little qualitative piece that comes from this skill is thinking about trends that we see in lattice energy. So there's 2 trends that I want you to think about, and you're going to see problems likely on your online quiz that'll ask you to rank who might have the greatest lattice energy. So there's 2 trends that we're going to consider, and I'm just going to give you a couple of examples to think about here. The first is ionic size. And again, I'm always going to be giving you examples here that are like the apples to apples comparisons. So for example, if I gave you this series, sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. What we can see here is as we go from sodium fluoride to sodium iodide, what's changing is the size of our anion. Okay? So what happens is as you get to a bigger anion, what happens is the lattice energy gets smaller. So the largest lattice energy comes from sodium fluoride. Now this is not unlike, remember when we talked about things in our last learning unit about electrons and protons, and we talked about them being attracted to one another. Well, this is still positive and negative charges that are attracted to one another. So the bigger, and kind of more lumberous that negative charge is, the harder it is to be interacting with the cation. And so lattice energy will decrease as we make one of those pieces larger. So the largest lattice energy comes from sodium fluoride, and then the smallest is going to be coming from that largest anion, that iodide. Okay, so this is that apples to apples comparison. I'm keeping one piece constant, the sodium cation, and then I'm changing the anion piece. So I'm not going to give you ones that are going to be really hard to determine because, well, what if I made the cation bigger and the anion small? No, you're not going to get ones like that. These are going to be pretty straightforward. Another example to go over is thinking about charge. So I'm going to give you another series here where I am maybe changing more than one thing, but we can see how they're changing in terms of charge. So let's look at sodium chloride, magnesium chloride, and then magnesium oxide. So if we want to imagine lattice energy kind of like being the strength between magnets, the stronger I make those magnets, the bigger the charge that I have there, the stronger that interaction is going to be. So for example, with sodium and chlorine, as sodium chloride, the charges are +1 and -1. This is going to have the smallest lattice energy here. Because when I go to magnesium and chloride, I'm going to have a +2 and a -1. And then with magnesium oxide, I'm going to have a +2 and a -2. So the greater the charges there are, the stronger the lattice energy, the bigger the attraction, the larger the lattice energy that we have there. So a little bit of qualitative stuff, but the quiz question that you're going to see is either going to be a problem like we're using Hess's law with lattice energy, or as we'll see in our next skill, it's going to be thinking about using bond energy with covalent bonds.